Good morning, everyone. As Paige said, I'm Corey Adams. In the ALCF, I'm a member of the data science group. I'm here to talk to you today about nuclear physics, basically, and neural networks. So just as a quick introduction, what's interesting about nuclear physics? Well, if you ask a nuclear physicist, they'll tell you everything. But the nuclear physics and the nuclei in particular is a very interesting regime where there's QCD, electromagnetism, all sorts of physics interactions going on. And it also gets really complicated because it's a quantum many-body problem. So we're studying nuclear physics to try to understand not just what's going on in the nuclei, but how does it impact our experimental searches for new physics in the laboratory. So this impacts things like the LHC, the electron-ion collider, neutrino-less double beta decay, DUNE, all sorts of things. Unfortunately, nuclear physics and nuclear many-body physics is really hard. It's a QCD problem. Everything is confined in terms of quarks and gluons within the hadrons. And there's all sorts of complicated interactions that you would need to go talk to the lattice QCD folks to learn more about. What I'm going to talk about today is what's called an effective field theory, where we just model interactions between nucleons with an effective 2- and 3-body interaction. And these potentials here depend on the distance between two nucleons. They have some experimentally fit constants, coupling constants. And these are fit to things like nucleon scattering data or the binding energy of oxygen. So at the heart of it, the nuclear many-body problem is solving the Schrodinger equation. And if you're not familiar with the Schrodinger equation, you'll probably need a textbook on quantum mechanics in a couple semesters to get into it. I won't bore you with it today. The challenge of it is that the exact solution to a many-body Schrodinger equation is exponentially hard, especially if things are correlated, coupled. And we're tracking not just nucleons in a nucleus in terms of their Cartesian coordinates, but also in terms of their spin and isospin. An isospin here is an effective parameter where if you flip an isospin, you turn a proton into a neutron or vice versa. So we're trying to solve this equation approximately. And while we're specifically targeting nuclear many-body systems, the things we've developed here for this technique are actually broadly applicable to quantum many-body systems. The technique we're using to attack this problem is called variational Monte Carlo. There's a really cool theory in quantum mechanics that guarantees that for any variational state, which is just basically a guess at the solution, you can calculate what the energy of that state is for your Hamiltonian, which we wrote down earlier in the talk, and that is greater than or equal to the ground state energy. So if you're able to update your trial variational state and minimize the energy, you can get closer and closer and closer to the ground state energy. And the wave function that you arrive at is actually unique. It's the ground state, and the lowest energy found is the best approximation. So if you can minimize this problem with some variational state, you can get a good approximation of the ground state energy. Unfortunately, in many-body physics, doing an expectation value with some sort of variational state gets exponentially hard. So you have to do these integrals in 3D per particle. So that's 3 integrals, 3 integrands times the number of particles you have. It quickly becomes infeasible to do this just directly or with some sort of numerical integration. So sampling these integrals to actually get to an estimate of your energy is computationally very, very hard. There is a way to do this from the central limit theorem. I have some backup slides if you want to talk more about it, but we can basically approximate this multidimensional integral through a technique that was developed back in the dawn of the first computers at Los Alamos. It's called, some people call it the Metropolis algorithm, named after this guy in Metropolis. It was actually developed by a number of people. Essentially what we do is we take some initial distribution of our nucleons and we just make up a position for them. We guess, maybe it's here. And then you compute with your variational state what's the value of your state at that position, and then you give it a kick. You move it around somewhere, some sort of Gaussian noise kick to every particle, and you compute again what's the probability that the state is like that. And if it's at a higher probability state, you move your particle to that state. And if it's at a lower probability state, there's actually still some probability that you're going to accept a move. And you can show, theoretically, that if you do this enough times for the appropriate size of kicks and the variational state, you will converge to a set of samples, we call them walkers, that are drawn from the probability distribution of your variational state. And this actually gives you the tool you need to do your multidimensional integral. You can sample from the variational state's probability space, and you end up with a way to compute the expectation value of the energy. This technique dates back to the dawn of the first computers, as I said. I think it's really cool that it's still in use today. And if you saw Oppenheimer this summer, one of these guys, Edward Teller, was in the movie, featured pretty prominently. And this is his spouse, and as well, the Rosenbluths was a pair. Okay, so assuming we have a technique to take a variational state and compute an expectation value of energy, we still have to talk about what do you use for a state. In quantum mechanics, there's this cool technique for anti-symmetry. So if you have two particles and they're interchangeable, your wave function has to go to 0 if they're at the same spot. It's called the exclusion principle, often named after Pauli. We can enforce this directly with this matrix here, S. It's known as a Slater determinant. Basically, the rows of the matrix are states, single particle states. The columns are individual particles. So if you take any two particles, you exchange them in this matrix, and then take the determinant, that's just flipping two rows or two columns of the matrix, and the determinant changes sign when you do that. So this gives us anti-symmetry built in. For example, the deuteron on the right, that's just two nucleons, a proton and a neutron. You would take the determinant of that small matrix there, just 2 by 2. But in principle, this scales to arbitrarily large matrices. So the challenge of nuclear physics is not just that each particle is in some orbital like an atomic potential, but also that the states are highly correlated. So finding a proton somewhere would mean that maybe you find a neutron that goes with it, depending on the nucleus. And you need a way to encode those correlations in your matrix, in your variational state, that you can't do just in your Slater determinant. So we introduced this additional term, we call it the correlator. It's this U function. And this U and all of the states in this matrix are encoded with neural networks. So this is just arbitrary feed-forward neural networks. They're not particularly complicated. And we put them into these states and construct a variational state. Because the determinant component is anti-symmetric when you exchange particles, we have to make sure that this correlator component does not do anything when you exchange particles, right? We flipped the sign already. We can't flip the sign again, or that would cancel out. And you can't have the wave function changing either, other than the sign change. So to do this, we put it into this deep sets formalism. If you're familiar with this, it's from a graph neural network, but it's basically a way to compute with neural networks fully symmetric output. So could be if you're working on point clouds and you want to have the points come into your neural network in arbitrary order, this is a useful technique. In our case, this gives us a physics constraint and says that the particles are totally identical under interchange in this correlator formalism. The exact details here, again, it's simple multi-layer perceptrons, machine learning networks. There's this phi network, which works on every single particle. And then we sum up the output of all those phis into a latent space, and we put it through another neural network. And that turns out to be enough to encode the correlations. Another thing we do that actually gives us a nice boost in performance is we can take the initial coordinates, if you have a nucleon at some Cartesian coordinate XYZ plus a spin and isospin, we put it through a graph neural network before the determinant and before the correlator. We actually replace the inputs to those components with the output of this graph neural network. And here we're using message passing graph neural networks. We've also used graph attention networks, looking into graph transformers as well. Message passing networks are kind of the state of the art in graph neural networks, so this turns out to be a pretty useful technique. Essentially what this is doing is for every particle, VI, and for every particle pair, Vij, you're computing an output you put that into a neural network and look at the output, combine those into a message, and then update the particles based on the message. So every particle is talking to every other particle for some number of layers. And the idea is with this message passing neural network, you're building into the correlations into your inputs to the rest of your neural network already. So this, when you combine this technique with the previous wave functions, this actually gets us to a universal approximator for a variational state. So in principle, we can solve any correlated state with this if we have enough computing power. The last thing I want to say about the wave functions themselves is you can't just use any old machine learning technique because there's some constraints that come from quantum mechanics. First, the wave function has to be twice differentiable, and it has to be continuous in the first derivative. So everybody's favorite activation function of ReLU doesn't work. That has a discontinuity at 0 in the derivative. So instead, we use things like tanh or sigmoid, and there's also continuously differentiable approximations to ReLU that work really well. Further, we add in a little term here, alpha times the sum of the R squared components. If you just try to solve a random collection of nuclei that you dump into a bucket, they will fly off to infinity in your metropolis walk. So we have to confine them initially, and the wave function actually learns to correct for this confinement exactly. But it's necessary to include this in the initial state, or else your algorithm will not converge at all. One of the last pieces of the algorithm is this technique called stochastic reconfiguration. If you're in a variational Monte Carlo setting, people know what you're talking about with this. The way I describe this is basically a second order optimizer instead of a first order optimizer. And one of the things that becomes different in variational Monte Carlo with these quantum states versus, say, training ImageNet is that the absolute value of the wave function doesn't matter. When we're doing our metropolis walk, we're only looking at the relative values, squared in fact, and the energy distribution doesn't matter at all what the absolute value of the wave function is. It only matters how it's changing. So this matrix is helping to correct for a lot of those spurious effects you see because of misnormalization or anything like that. But it's a complicated algorithm to do computationally because you end up having to invert this matrix S. So the updates to our parameters in the variational state, instead of just being their initial values minus some learning rate times the derivative of the energy with respect to the parameters, we have this matrix inversion too. And to compute this, that actually requires the Jacobian matrix of the entire network. And if you're familiar with the Jacobian, you can imagine training something like a large language model with 1 billion parameters, giving you 1 billion times 1 billion matrix for the Jacobian is just impossible. I don't think we have enough computing power to do that anywhere yet. So this limits some of our size of our neural networks. Typically, we're looking at 10 to 20,000 parameters. I think our largest network we trained is 50,000 parameters, which is a stark difference from the trillion parameter work going on. Okay, so just as a summary, we have this trial wave function, our variational state. We create a set of called walkers to do the numerical integration, and we use as many of those as we can possibly fit on our hardware. We thermalize them, which is just going through this metropolis algorithm to make them be drawn from the probability distribution. And then we compute our observables, things like energy, the gradients, the Jacobian that we need for this reconfiguration matrix. And then we update our wave function. So it looks kind of like this. You'll thermalize initially for a couple thousand steps, and then you just do this iteration until convergence. Measure your observables, update your parameters, then thermalize again, because once you've updated your parameters of your variational state, your walkers are no longer consistent with that probability distribution, so you have to correct for that. We do this until convergence, which sounds simple, but it quickly becomes computationally challenging. We initially did this in PyTorch. So when we started this work, JAX was not really a big thing yet. It was just starting to emerge. PyTorch is imperative. So when you call an operation in Python with PyTorch, it goes off to the GPU and does that right away. And now they're looking at compiling and optimizations, but when we started this, it would wait for the GPU to finish, and then it would return. And when we needed to do something like 5,000 thermalization steps, calling a small machine learning model each time, it got very slow. So PyTorch was inefficient. libtorch, which is PyTorch's C++ front end, was a little better, but it actually had some major concurrency issues when computing the Jacobian matrix. We tried it. It was super slow. Generally, Torch is really good when each op on the GPU is big, or if you need to prototype something really quickly, but it fell over here. And TensorFlow did a little better, had really good scaling properties, but as our number of nucleons grew, the graph compilation stage in TensorFlow was actually timing out our job. So a 1 hour job would not finish the graph compilation stage. So that was not feasible either. We switched to JAX, which is one of the newer machine learning frameworks, which is really great. It lets us compute the Jacobian easily. We can get the first and second derivative of our wave function, which is a machine learning model with respect to the input variables. We need the second derivative actually to compute the kinetic energy. If you're familiar with quantum mechanics, you'll recall that the kinetic energy operator is proportional to a second derivative. JAX also gave us an easy way to compile a lot of our small operations into one XLA graph. It was very easy to vectorize everything. And in short, if you have any sort of machine learning algorithm that you would say is weird, and by weird, I mean it's not equal to ImageNet or a large language model, JAX is really awesome. So I see it cropping up in differential equation solvers and all sorts of places. Here's one of our first results, solving the deuteron. So that was just 2 particles. You can see in this zoom in here, this dashed line is the exact energy of the deuteron. And our wave function was approaching it exactly after just 500 iterations. So this was a nice result initially. This was a couple years ago at the start of COVID. We then started scaling up to nuclei, up to 6 particles. Our wave function scales as a to the 6. So, I'm sorry, a to the a cubed. So 6 particles was still feasible at this time. As we got better techniques, it got better and better. But our values here for the ANN, artificial neural network computed energy, were actually matching up with the experimental values relatively well, especially when we included the 3 nucleon potential. As well, helium was one we liked to showcase because we solved for the energy. We optimized the energy of the variational state, and then we computed what the probability was to find a nucleon at any particular point out from the center of mass of a nuclei. The blue curve here is from Green's field Monte Carlo. It's basically an exact technique for small systems. Our neural network matched it, not just where it was large, but out in the tail over 4 orders of magnitude, which was a really satisfying result. So we can solve helium exactly. It wasn't super interesting, except as a technique demonstration, but now we started looking at scaling to larger and larger nuclei. So the way you do this is, as you get to a bigger system, you need more walkers because you just need more statistics, you need a more complicated wave function, you need a better sampling of your integral. The challenge is, as the number of walkers increases, which is the number of times we're sampling that multidimensional integral, it increases both the computational time and memory usage. So here is just as a function of the number of nucleons, A, on the x-axis, how long it takes per iteration as you increase the number of walkers. So down here in the lower left corner is something like 8,000 walkers, and you can only get up to A equals a small number, less than 10. And to get to nuclei that are experimentally interesting for nuclear physics, you're looking at 1, 2, 4 walkers will fit on a single A100 in this case. So this was a clear need to parallelize the algorithm. As well, your computational time starts to increase. So just putting more walkers on a GPU at first doesn't give you a substantial increase in computational time until the number starts to get large. And then, in this case, it was the thermalization, the walk, that was really driving up the computational time. But as I'll show soon, when you parallelize, other things start to dominate. So I talked about the algorithm's design. When we looked at how to parallelize it, some things were easy, right? If you're doing a multi-dimensional integral and you're sampling it 1,000 times, put 5,000 samples here and 5,000 samples here, and it's parallel. That was easy. Computing the observables turns out to be a collective operation because there's some normalizations you have to do. You have to get the whole integral together, and then you can normalize your Jacobian properly. But that's not so bad. That's just one all reduce. Our main challenge is this stochastic reconfiguration step. So if you recall, we're solving this equation, S times the initial gradient equals the gradient we actually want. Sorry, let me say that again. S times the gradient we actually want, the second order one, equals our initial gradient, just the derivative of the energy with respect to the parameters. Inverting S gets challenging. That S matrix is in principle a square matrix the size of the number of parameters on each side. So if your network gets too big, you can't even construct it in memory. We get around this with a conjugate gradient method, so we can reduce our memory usage, but then it has to take a couple hundred iterations of conjugate gradient to solve it. And at each iteration, we're doing a collective operation. It's a small collective. It's only 10,000 parameters, 50,000 parameters, not huge for supercomputing, but if you do it 200 times per update of your weights, it starts to add up. And that's what we see on Polaris. So here's how we scale up on Polaris, going up to half the system in this plot. In green on the bottom is just the time it takes for us to thermalize before we do each numerical integral. In red is the time it takes for us to compute things like the energy, the kinetic energy, and everything else like that. And the reason that dominates is because there's a point-to-point interaction, and we actually have to do things like swap two particles, recompute the wave function, and the number of computations you do here scales as the number of particles squared. This optimizer step in sort of dark teal is what's growing as we scale up. And that's because that collective, where you're doing a conjugate gradient step as you all reduce the weights of the model, is getting longer and longer with more and more nodes. So on Polaris, we're up to 80% scaling efficiency at half the system, and it's hard to improve that without sacrificing accuracy. So that's where we're at on Polaris. We can solve nuclei quite efficiently up to about A equals 40, so that's calcium, and that's that regime. We've solved it on Polaris already. We're still cross-checking the results before we publish it. But this is giving us really cool collaborations with some of our nuclear experimental physicists over in the physics division as they collide two nuclei and measure the density of the nucleons. We can go compute the wave function that they're measuring and say, does it match or does it not match? Is our model good? Is your experiment good? Probably their experiment is right. They're good at their jobs. With Aurora, we're looking at being able to solve up to hundreds of particles in one system, down to an exact ground state as good as we can get with our Hamiltonian. The biggest challenge is ensuring that this inversion of this matrix scales beyond 1,000 ranks. So, of course, it can scale, but if it's taking 10 seconds per update, it starts to become detrimental to the convergence of the algorithm. And we're also looking into applying these techniques to different Hamiltonians. So not just nuclear physics, but you could put this in molecules and do electronic states as well. Okay, so thank you, everyone. Happy to take questions.
Thank you, Corey. We have time for probably one question, and then Corey will also be around for the rest of the day if you want to pester him otherwise. Any questions?
So the overall scaling is still n to the cube, similar to quantum Monte Carlo.
Yes. What's the question?
Yeah, so is that the scaling factor is getting much smaller compared to traditional quantum Monte Carlo?
I'm not sure. Our scaling factor will probably stay in the A cubed regime. I think the biggest enhancement we get is we can do direct spin coupling in our Hamiltonian, which I don't know if you can do in quantum Monte Carlo as efficiently. And we're also finding that we get results at better convergence with our variational neural networks.
Excellent. Okay, thank you, Corey.
Thanks.
Let's thank him again.